Assalamu alaikum. Today we're going to be discussing the other topics related to simple harmonic motion. Earlier we have discussed the various parameters of simple harmonic motion. Today we will discuss like kinetic energy for a particle executing simple harmonic motion. What's the potential energy for a particle executing simple harmonic motion? What's the time period? We're gonna be discussing those things today as well. So let's start with restoring force. Restoring force. When we apply force on a body, the body gets displaced from its mean position to some other position. And when we apply force, body tends to come back. There actually a force comes into play, and that force actually tends to bring the body back to its mean position. And that force, we call that force as restoring force. So restoring force is a sort of force which tends to bring the body back to its mean position, and this force is denoted by Fr. So let us suppose there is a body of mass m, and we apply force on this body, and we have to calculate the restoring force for this body. So this restoring force can be calculated as like this. As we know, force is equal to mass and acceleration. So this will be the mass of this body which is executing when we are applying force on this body, and this body is getting displaced from this position to let us suppose this gets displaced to this position. So when this body reaches to this extreme point, a force comes into play. That force is called as restoring force, and this force tends to bring the body back to its mean position. So to calculate this force, we're gonna be using the simple equation F is equal to ma, where Fr is the restoring force, m is the mass of this body, and acceleration, we already know acceleration is actually equal to a equal to minus times omega square y. So Fr will be equal to m minus times omega square y. So restoring force will be equal to minus times m omega square y. So this is the equation for the restoring force. Now you already know that force is actually equal to minus ky. For a particle to execute simple harmonic motion, force should be in this form. F is equal to minus ky. So let's call this equation as equation first and this equation as equation second. So if we compare equation first and equation second, then we will find that k is actually equal to m times omega square. K will be equal to m times omega square, and this is the one of the important results that came out of this restoring force. So this equation will actually help us to find the time period as well. So let me first rub this. So k is equal to m times omega square. K is equal to m times omega square. So omega square will be equal to k divided by m. So omega will be under root of k by m. Omega is actually equal to 2 pi divided by t. It's actually angular frequency, and angular frequency is equal to 2 pi divided by t, where t is the time period. So let's replace omega by t pi by t. That will be equal to k by m. by doing reciprocal on both the sides of this equation, we will get this result. T will be equal to 2 pi under root of m divided by k, and this is the equation for time period. Equation for time period of a particle executing simple harmonic motion. Now let's calculate the kinetic energy of a particle executing simple harmonic motion. Let's take an example of a body of mass m and velocity equal to v. As we know, kinetic energy is actually equal to 1/2 of mv square. We will replace this v actually using this equation, v equal to omega under root of a square minus y square. So kinetic energy will be equal to 1/2 of m. We will replace v by omega under root of a square minus y square. Omega under root of a square minus y square whole square. So this will be equal to 1/2 of m omega square a square minus y square. This m omega square is equal to k, as we have learned this as well. K equal to m omega square. So 1/2 of k a square minus y square. This is the equation for kinetic energy of a particle executing simple harmonic motion in terms of displacement. Now, in order to calculate the kinetic energy in terms of harmonic functions, we have to replace this this velocity, this v, by using this equation, v equal to a omega cos of omega t. So kinetic energy will be equal to 1/2 of m a omega cos of omega t whole square. So this will be equal to 1/2 of m a square omega square cos square of omega t. So this will be equal to 1/2 of m omega square, that is equal to k omega square. We will replace this cos square of omega t by using the equation half angle formula, and by using that equation this will be equal to 1 plus cos of twice omega t divided by 2. So this is the equation for the kinetic energy of a particle executing simple harmonic motion, but in terms of harmonic functions. So clearly you can see that if a particle is executing simple harmonic motion with frequency omega, and its kinetic energy actually oscillates with double the frequency, double the actual frequency. It oscillates with the frequency 2 omega, and in this case, if the particle is executing simple harmonic motion with time period t, the time period gets halved and it becomes t by in case of kinetic energy, it gets halved and it becomes t by 2. So kinetic energy oscillates. When the kinetic energy oscillates, the frequency gets doubled and the time period gets halved. So this is about kinetic energy. Now let's move on to the graphs. Now let's study about the graphs related to kinetic energy. First, let's write the equation. Kinetic energy equal to 1/2 of k a square minus y square. So let's plot the graph between the displacement and kinetic energy. Let us suppose x axis represents the displacement and y axis represents the kinetic energy. And if we plot the graph, and graph will be like this. So this graph clearly depicts that kinetic energy is maximum at mean position and minimum at extreme positions, and is actually zero at extreme positions. It's because of the fact that we have already learned that velocity is maximum at mean position and is very minute, and it's actually equal to zero at extreme positions. So this was the graph between kinetic energy and displacement. Now there is other graph of kinetic energy, and to draw that graph we have to write the equation of kinetic energy in terms of harmonic functions, and that equation is kinetic energy is equal to 1 half of k a square cos square omega t. So using this equation we will plot a graph between time and kinetic energy, and the graph will be like this. Because here the power cos is raised to the power 2, so the we have to take the positive side of the graph. We have to take the positive x-axis this side of the graph, so that's why the graph comes out to be like this. And the time period for this is actually t equal t by 2, because we have already learned that kinetic energy in case of kinetic energy, the time period gets halved and the frequency gets doubled. So f dash is gonna be 2f and t dash will be equal t by 2. So this was about kinetic energy. And